Okay, I'm going to talk about molecular recognition using nanomechanical photothermal effects. So before I go, there are lots of people who contributed to this work, and it's mostly a collaborative work from Oak Ridge to with Alberta and so on. So outline for the talk, I'm going to talk about traditional MEMS sensors, cantilever based. Then I go to receptor-based type sensing, chemical sensing and biosensing, and then introduce the concept of photothermal effects in MEMS. Then go to receptor-free sensing, and then go into a couple of different development that we can pursue after this, including the standoff photothermal spectroscopy. Here, this is now there is a big push towards detection of different vapors for disease detection, and we kind of know different biomarkers, volatile organic compounds are associated with these diseases. This is all in the literature. There are lots of literature in this area. So we basically develop microfabricated cantilevers, which look like a little diving board. And we immobilize some kind of a self-assembled monolayer or some kind of a physical or chemical interfaces that it can interact with the specific analyte molecule. And you look at two things. One, you can look at the mass variation from the frequency shift. And you can also look at the bending, provided only one of the sides of the cantilever is immobilized with the receptors. The part I will be focusing towards the middle of the talk will be how this can be used as a thermal sensor by making it bimetallic. So this is the basic theory. This is approximate equations. We don't have to go into details to understand what is happening. Z, which is the bending, is directly related to the change in surface energy, and it is amplified by the length over thickness square. And you can make chips. These are maybe 3 millimeter by 4 millimeter chip. There are 32 different cantilevers here in this microfluidic well, all electronic readout. And you can have different coatings or the interfaces on different cantilevers. And as a result, you can see a response pattern for specific molecule or a mixtures of molecules. And here is an example for PETN, which is explosive vapor form. And this cantilever is, this is an old result, immobilized with mercaptobenzoic acid, which is very selective, somewhat selective to explosives. And this red line you see is the point where the bending of the cantilever, we inject PETN without changing the flow rate. Cantilever bends, reaches a steady state. We turn off the PETN and it returns back. These blue dots that you're seeing are the Brownian motion of the cantilever, the resonance frequency that is shown here. So this bending is due to the energy or change in surface energy of the cantilever due to molecular adsorption, while the blue dots are the mass variation due to adsorption. So these are two orthogonal information that comes at the same time. And you can make into, expose it to different gases. In this case, all these cantilevers are modified with the different polymers or self-assembled monolayers. And I'm showing only 4 of them. And you can see response to acetone, ethanol, water, TNT, toluene, unknown vapor. And then you can do the machine learning or neural net analysis and different type of pattern recognition concept and then try to understand what is the unknown vapor. This works for a while until it gets too complex. Then it doesn't work anymore because machine learning cannot do anything after that, because chemical sensing is based upon molecular interaction, and all the molecular interaction for reversible sensing is based upon physisorption, where the energy of absorption around kT, 10 to the power minus 21 joules also. So you can see that most of the molecules absorb with the physisorption, either van der Waals interaction or hydrogen bonding. And if we go up in energy, as shown here, then it becomes irreversible. So it works only one time. So this is not a good idea. If you make it a high reversibility, then selectivity is also low. The three rules of chemical sensing is selectivity, selectivity, selectivity. So unless we have selectivity, there is no sensor. So we decided to go with a different approach, where we have this bimetallic cantilever. We basically deposit a thin layer of metal, like gold or aluminum, and this is the sensitivity of the cantilever, thermal sensitivity as a function of thickness of metal. And this all modeled very nicely, and it's become extremely sensitive to temperature in the range of millikelvin without any cooling. So it's a thermal sensor. So we can take this thermal sensor, expose it to different wavelengths as shown here. This is the cantilever bending when we expose the cantilever to 200 to say 900 nanometers of light from a mercury light source. And you can see that all the mercury lines you can see as a bending in the cantilever, because of the more photon comes in, more heat is produced on the cantilever. So we used this approach to look at the molecules, because in the mid-infrared range, 3 to say 14 micron, these molecular vibrations are free of overtone. So we can basically identify the compounds using this concept. Only thing we have to do is expose the cantilever to different wavelengths, scan it, or you can have different cantilever arrays and then use a grating to expose different wavelengths to different cantilevers. And what happens is that non-radiative decay produces lots of heat in the cantilever, very small amount, of course, and that when cantilever bimetallic cantilever will bend according to the number of photons or heat generated by the cantilever. So this is an example. We're looking at the TNT absorbed from the vapor phase, and you can see that this is the bending of the cantilever, and you can see these two the lines are very characteristic of the TNT, and this is the baseline, and this is PETN, which is another explosive, and again absorbed from the vapor phase, and you can see the very beautiful curve, the spectrum, mechanical spectrum. Now you can use TNT and PETN vapor adsorbed on the cantilever, and you can expose two different wavelengths. Again, you see looks like a linear combination of TNT and PETN spectrum. So this is but very exciting in the sense that you don't need any chemical interfaces for selectivity. You can basically use physisorption on the surface and exposure to light, different wavelengths. You can also do very complex molecule like a naphtha. Naphtha is like a kerosene, and this is the cantilever bending as a function of different wavelength. And this is the light source is a glow bar with a filter wheel, and you can see all the lines. And this is from ATR, and this is a FTIR, and I have identified all the bonds here, and we can see all of them. And you may ask the question why this is cantilever is not, I mean, fine, does not show any fine resolution because our slit was a little wider, and because the glow bar is a weak light source, and these are very sophisticated light sources. So this is the picogram amount of material. This is in the milligram amount. So you can see that the orders of magnitude in sensitivity also. You can also detect things that does not absorb, like methane, CH4. But however, CH4 has some residence time depending upon the heat of absorption on the surface, and it may stay on the surface for nanosecond. So during that time, we can expose the cantilever to, of course, they are absorbing and desorbing, and this vibration, the time is so fast, so you can see the spectrum of the methane. And this is taken with a quantum cascade laser, and the amount of methane absorbed on the surface is 18 femtogram. So the question is whether we can detect, for example, liquids. Of course, we can also detect liquids photothermal way. This is a cantilever. We made a little microfluidic channel in it, and this is a channel. You can see the CM picture. This is the channel cross-section, actually. This is idea actually developed by Scott Menalis at MIT, and this is the famous Nature paper. So you can actually push the liquid through the inlet as a flow, or it can be, non-flowing phase. Either way, it works. So you can do multiple things with it. One, for example, you can get the density measurement from the resonance frequency. You can also look at viscosity if you know the key factor of the resonance. You can also expose it to different wavelengths, the IR, UV, visible, and so on, and get a spectrum, molecular spectrum of the chemical inside it. You can also look at the thermal diffusivity of the liquid, for example, shining with a pulse heating, and then look at how the response changes with time. And here is the making it more sophisticated. So this is a fluidic cantilever actually, and in this case you need a laser Doppler vibrometer to see it. And now this whole cantilever is in vacuum, but the inside of the channel is open to air basically, so or air or liquid. It needs some complex, not that complex, optical arrangement, and you can see that this is the cantilever resonance frequency, 0.6 to 6 megahertz, with the quality factor around 6,000 to 13,000. And you can see that this is the resonance spectrum. It's a beautiful curves. And so you can do lots of very, very interesting experiments. So one of the experiments that we did was not using the vacuum arrangement. This is the cantilever actually, hollow channel cantilever exposed to air. Inside is the liquid. We immobilized with some peptide to trap this bacteria. And so you can enrich the sample. And after that, you can measure their mass, then look at the bending of the cantilever to binding. And you can also expose to infrared wavelength and get the spectrums of the bacteria. So this is a paper we published in Nature Communications. And so now we can take this bacteria and do something interesting, because the bacteria produces around 10 to the power minus watt of heat because of the metabolism. And the heat can appear as a noise on the cantilever. So we can give them some PBS solution. And so this is the noise spectrum that we see. And then we can give them some sugar solution. So they metabolize the sugar very fast, and you can see the noise. The bacteria is very active now. Then you can inject some drugs, for example, ampicillin, and then you can see that the bacteria dies practically. This is the ambient noise of the cantilever because of the thermal energy KT from the ambient. We have, you can also use different drugs like a clindamycin, And you can see that kinomycin has no effect on the bacteria in this case. And we have confirmed this with looking at the fluorescence data. So you can also do all kinds of the drugs or whatever chemical. You can, the volume of this channel is around 50 picoliters, and you can fill it with say amphiphilin sodium salt and expose it to different wavelengths, and you can see the spectrum. So this needs a little bit more improvement in the sensitivity, but this idea works even in the liquid phase. This is again photothermal spectrum of fumarate and the glucose, 50 picoliters, and this is 10.5 millimolar, and the glucose is around 5.4 millimolar. And you can see the spectrum very clearly from scanning the wavelength. So we also developed a little mass spec arrangement. Basically use a capillary electrophoresis. We use the egg white. This is the standard spectrum for egg white. We have done gel electrophoresis, and we can actually separate the different proteins in the egg white. This is the egg white, and then actually inject through the basically through this little the hollow channel cantilever, and look at the resonance frequency as a function of time. So it's like more like a time of flight mass spec, and you can see as the different protein groups coming through the cantilever, the resonance frequency changes. And this is the standard spectrum that we got for egg white, and you can see all the blobs here we can identify in the resonance frequency spectrum. Now we are trying to do what the photothermal spectrum of these different proteins as they come through it. So the advantage of this technique is that you can actually do, generally mass spec need a vacuum, but this can be vacuum sealed in a chip level. So the cantilever is in vacuum with a high resonance frequency and high Q factor, very high sensitivity for mass, but the inside is open for liquid or bringing different proteins and measuring their mass, and also infrared spectrum using photothermal concept that I talked to you about. You can also do DNA unraveling. You can take a double-stranded DNA and you can make it come apart, and then we see very interesting things. Generally, people see one, sigmoidal shape response. We see more additional, like a more statistical process that is taking place as the DNA unravels, whether it is like a zipper or bubble formation and things like that. So we can also do the photothermal as it unravels. We haven't done the photothermal yet. It is in the works. It doesn't have to be cantilever. It can also be nanowire. This is a bismuth ferrite nanowire. We have suspended across 2 electrodes. So this is a suspended nanowire. It has a very low thermal mass compared to that of a cantilever. So now what we can do is that we can do the same thing, but however, measuring the resonance, mechanical resonance, become harder because the wires are so narrow. So nanometer size wire, this is maybe micron, and a couple of micron. I don't exactly remember the radius of this thing, but it's very difficult to focus light and get the resonance, mechanical resonance spectrum. But what we can do is that we can look at the electrical resonance. We can make a model, lumped oscillator model, and then measure the electrical resonance. Remember that since the thermal mass of this whole thing is very small, nanowire is very small, it responds very fast compared to that of a cantilever or a bigger device. This is also published in Nanoletters. So here we have done some adsorption of, say, for example, RDX. And you can see we are showing us a dissipation of the resonance spectrum, electrical resonance. And you can see the spectrum of the RDX. And here we are comparing the same thing with that of a FTIR. You can see that FTIR still has some kind of finite width compared to that of our electrical resonance of the nanowire. This is mainly because of the mass of the device, you know. And we can also go into the I didn't explain that this is also again nanowire is exposed to different wavelengths of light. This is again a photothermal spectrum. And here is a nanowire that is suspended or microstring. This is vanadium oxide. So it will show what you call the metal insulator transition. And as shown here, this is the temperature, and this is the resonance, the electrical resistance. That shows a very sharp decline at the phase transition, the metal to insulator or insulator to metal transition. And this is the resonance frequency of the device, the wire, which is taken with a laser Doppler vibrometer. And that also shows some curve like this. Now we can actually heat this thing using different lasers. So we used a couple of different red, green, and blue lasers, visible lasers to heat it. So we can actually see this curve actually goes through this transition. And we haven't been able to expose it to infrared because this is in vacuum. And of course, we don't have a zinc selenide window at this moment in time to expose it. So another idea that we can do is also standoff spectrum. For example, you can have a quantum cascade laser shining at the surface, look at the scattered light, and then collect the light, and then expose it, expose it that to a bimetallic cantilever, or the cantilever is acting like a mechanical detector here in our case. And you can see the low density polyethylene and PVA is taken out, say 10 to 15 centimeters away. We can increase the distance even further. So this is the cantilever bending as a function of different wavelength. So we are illuminating the surface, faraway surface, with this quantum cascade laser, and which basically tunes the wavelength 1400 nanometers to 1150, and it shows the nice spectrum. So this is a real plastic sample that we are trying to do for the plastic sorting, because the sorting plastic is important for the recycling. And if you can identify which plastic is coming through very fast, we should be able to sort it out much faster. So this is, 25 minutes, so I will conclude my talk here saying that nanomechanical IR photothermal spectroscopy provides a receptor-free approach for chemical selectivity in MEMS and MEMS. Hollow channel cantilever allows photothermal spectroscopy of confined and flowing liquid samples. Nanowire can also be combined with electrical resonance. This offers another opportunity to develop new devices. We can also use metal insulated transition of thin films like vanadium oxide. Vanadium oxide here is only 20 nanometers, but it can still show the transition. And this vanadium oxide is deposited on a silicon nitride microstone. And I also showed that it can be used for standoff sensing. So there are many different possibilities using combining light and mechanics here. So I will stop my talk here, and we have enough time for questions.